In the last session, we discussed dbScan, a density-based clustering method. For the same group of authors, they later invented another interesting algorithm called optics, ordering points to identify clustering structures. Why they want to do that? Just because dbScan is sensitive to parameter setting. So optics extended dbScan, but make it is much less sensitive to parameter setting because it can find a clustering structure. This algorithm was developed by almost the same group of authors in SIGMOD 1999. We can have a simple observation. Suppose we fix one parameter of dbScan, say minimum number of points. Then for density-based clusters with respect to high density, that means you just need a small radius to cover the number of minimum points, like 5. These dense clusters are completely contained in clusters with respect to a lower density. Simply says the dense cluster is deeply nested in the less dense clusters because less dense cluster needs a bigger radius to cover the same number of minimum points. So if we observe this one, we probably can see we may have high density points should be processed first or deeper in order to find a high density cluster first. Then we can plot them into a reachability plot for a data set. Optics actually stores such a clustering structure using two pieces of information, core distance and a reachability distance. We will introduce in the next slide. But let's look at this reachability plot. If we got this set of data sets, then if we study their reachability distance, since the points belong to a cluster have lower reachability distance to their nearest neighbor, simply says you just need a smaller disk to cover the minimum number of points. So your epsilon, this disk radius, should be smaller. That means the valley should contain the very dense clusters. Okay, the deeper the valley, the denser the cluster. So you probably can see if we order them according to their reachability distance, we probably can plot them into a graph so you can easily find the clustering structures. So that's the trick of optics. Then let's look at how optics is defining core distance and the reachability distance. We first look at the core distance. For core distance of object P, like this one, is the smallest epsilon value, okay, such that P's epsilon neighborhood will contain at least the minimum points objects, for example, 5. Let's see. If you say P, you try to find its radius to cover 5 points, like 1, 2, 3, 4, 5 points. Now you probably can see this epsilon should be 3 millimeters. Simply say 3 millimeter, you will be able to cover 5 points. That's actually is the definition of the core distance. Simply says if P is so isolated, you just cannot find enough neighbors to cover the minimum points. Then we say this core distance is undefined because you stretch so large, you just cannot find enough neighbors. Okay. On the other hand, okay, if you can find a minimum number of points, then this minimum number of points distance of P is the core distance. For example, here, like this P, you just need a 3 millimeter to cover this, then the core distance is 3 millimeter. Then we look at reachability distance. The reachability distance is from a core object Q. Reachability distance of P, you want to reach this Q, what you want to define is the minimum radius value makes P density reachable from Q. If you want to see if P can reach Q, okay, from Q, then you just see if Q is not a core object. Simply says no matter how big you stretch, you just cannot have enough object to get a minimum number of points, then this reachability distance is undefined. Otherwise, okay, you just see which one is bigger. Is the core distance is bigger, or the distance from Q to P is bigger? Okay. For this picture, you can see is if you look at the reachability distance from Q to P rather than from P to Q, we just look at from Q to P. If Q1 to P, is smaller than the core distance, then the core distance should be the reachability distance. Otherwise, like this Q2 try to reach P, okay, then it's bigger than the core distance, then the reachability distance is the distance between P and Q2. So that's essentially the definition of reachability distance. That means how big your disk is in order to reach enough number of minimum points. To calculate this, the complexity is n log n if you have index. N is number of points, so it is not too bad. Then based on this idea, we actually work out this clustering structure. The structure graph, the nice thing is this method produces special clustering ordering of the data points with respect to density-based clustering structure. Then the clustering structure actually, it contains information equivalent to density-based clustering corresponding to a broad range of parameter settings. For example, the first thing is you fix minimum number of points, you get this plot. And with this plot, for example, you see there are 4 major clusters. If you do not think this one is something, you actually can find 1, 2, 3, 4 clusters. Okay. Even you change the number of minimum points, okay, you will still be able to find the same number 1, 2, 3, 4. Of course, the plot is somehow change the shape with the different minimum number of points, but still you can find 4 clusters. Moreover, you can find nested clusters. For example, this bigger cluster has 3 deeply nested clusters. You look at this bigger cluster, it contains, if you see the deeper one, you see 1, 2, 3 deeper clusters corresponding to this. So you probably can see this is very nice. You use different line on the epsilon, you actually can find the bigger cluster and nested clustering structures. So it is a pretty interesting algorithm, and you can actually use automatic or interactive. You do clustering analysis, you can find intrinsic, even hierarchically nested clustering structures. So this is a pretty interesting extension to DB-SCAN. That's the optics algorithm.